Hi class, this will be the last lecture for the lab series. So in this lab, we will talk about a molecular model. You may wonder why we talk about a model. A model, according to the dictionary, can be a three-dimensional representation of a person or thing or of a proposed structure, typically on a small scale than the original. Now this is one type of explanation for model. And in this case, the model we can also call like a copy or representation or dummy imitation, something like those words are similar to this definition. Another definition about the model will be a simplified description, especially a mathematical one, of a system or process to assist in calculation and prediction. Now, words similar to this definition are some like a prototype, stereotype, a type, version, style, something like this. You can see those words. Now, in terms of the molecular models, we will say that will be the simplified description of the molecular geometry that allow us to image how the structure looks like. Remember, molecules are formed by very small atoms, right? And our eyes cannot be able to see it. So that helps us to figure out what's the structures. We need to have some imagination, and so we need to use the model to help us to understand the geometry and the structure of the molecule. That also help us to understand the many chemical and physical phenomena regarding the molecules. So let's look at the example of illustration. As I mentioned at the beginning of this class, we will ask you to use critical thinking. And critical thinking, we will ask a student to adapt to a style of SEEI. So this abbreviation, S stands for state. That means you need to be able to express something definitely or clearly in speech or writing. So you can write, for example, the definition of something. So that stands for state. First E stands for elaborate. That means based on the statement you provide for a particular object, you will be able to add the more details concerning what has been said. So that's for the elaboration. Then this one is basically to provide the example. So the last one, I, means that illustrate here, or you use noun, that will be illustration. This one means to explain or make something clear by using examples, charts, pictures, etc. Right now, we are facing the challenge about the coronavirus. So in order to talk about what's the coronavirus, so if you apply the critical thinking, for example, you need to say that any of the family of single-strand RNA virus that have a lipid envelope started with a club-shaped projection, then that kind of object or structure can be considered as a coronavirus. Now to elaborate that, you can say coronavirus can cause a variety of illness in animals, but in people, coronavirus causes 1/3 of common colds and sometimes respiratory infections. And we often see, and for the example of the coronavirus, you can list them. Maybe that's, for example, MERS, SARS, or currently the COVID-19, right? Now, to illustrate that, you can provide the image or chart about what the coronavirus looks like. For example, here, so you can show people this is something the coronavirus looks like. And you can see that we say here, this will be the RNA structure, right? And then you can see that's the envelope, that's a lipid envelope. So we have those things where you can see this one is a hemoglobin esterase dimer for this case, and the spike glycoprotein for this one. And currently, to solve the coronavirus COVID-19 problems, people suggest use one of the medicine called chloroquine. So the structure of that one looks like this one. So you can show the structures. Now let's come to our problem. Why we need a molecular model? As I mentioned earlier, the molecular model will help us to provide the physical representation of the three-dimensional arrangement of atoms in space. And remember, all the atoms are so small which our eyes cannot see. Think about the scales. So let's say the bacteria. The scale is somewhere like 2 micrometers. So this one is roughly about 2. And the virus are even smaller than the bacteria. We will say atom is 1 angstrom scale. That was roughly about this one. You can see this case. It's about 20,000 smaller than the bacteria. So even bacteria we cannot see from our eyes. The atoms even smaller. Also, the molecular model can provide a three-dimensional image, either physical or software-based. So you can actually use some kind of model kit to build a molecule, or you can use software to generate a model that allows chemists to better see the manner in which atom and molecule can interact. So this case, just like the structure I showed earlier, for the chloroquine, you can see the geometry, how that can interact. And the molecular model can also provide detailed information about how atoms interact with each other at the atomic level. You will see more examples later on when we talk about how the polarity of the bond or the molecule can affect the physical property of the molecules. So there you can see how those atoms interact with each other. And also the molecular model can help us to better understand both the chemical and the physical property of the molecule encounter. So this we will focus on later on. And also the molecular model can interpret the observations or to predict the new chemical behaviors. For example, if you study some particular molecule, you found out that there are unique physical properties, and you can use the molecular model to explain that why that particular molecule has such a unique property. For example, we mentioned alcohol, like ethanol. Right? We know ethanol right now, you use 75% of ethanol eradicated some of the COVID-19, right? So you may ask, why is that? You can see the ethanol as an organic solvent can dissolve the shell of the virus, can damage the virus. Now let's look at the atomic model. When the molecules are composed of atoms, the atoms are joined together by chemical bonds that are more difficult to break. In this case, when we talk about here, chemical bonds, in your general chemistry, you may have studied the ionic bond. Or covalent bond. As well as a metallic bond. Now you should be familiar with the periodic table already. So the ionic bond actually formed between the metal elements and the non-metal elements. Because in this case, metal elements likely to lose their outer shell electrons, and the non-metal elements like to gain the electrons. So in this case, they involve electron transfer, right? So that can form the ionic bonds. So that's basically a metal lose electron and will be oxidized to form the cation. And the non-metals will gain electron to form an anion. So anion carry negative charge, whereas cation carry positive charge. And we know that positive charge and the negative charge will attract together by electrostatic interaction. So that's how we call ionic bonds, right? Now for the covalent bonds, basically formed between the non-metal elements. So in this case, we will talk about them. You will see later, most of the cases when you study the bonds, actually are covalent bonds. So that's how we will focus for this class. Now, covalent bonds formed between the non-metal elements because both elements want to gain electrons and then none of them is likely to lose the electron. So in order to form the bond, so they share electron. That's how we call covalent bonds. So that means they share, so covalent bond. So the co means share. All share their valence shell electrons to form the bond. So that's how we call covalent bond. Now, metallic bond basically formed by the metals. Like we have all kinds of metals. So that will be the metallic bond, and this will not be the focus for this class. Now, each individual atom consists of smaller particles, basically we call electron and nuclei. Now, if you check the periodic table, you know that for each element contains a different number of electrons, and so there's different number of the protons. According to the number of protons, the elements are arranged in such a way so they can be put into the periodic table, right? And every atom should be neutral, so the number of electrons equal to the number of protons. However, we know that the protons and the neutrons are located in the nuclei, whereas the electrons are found in the atomic orbitals. Starting at the lowest quantum number, that's basically n. We know the quantum number starts from n equal to 1, 2, 3, 4, right? So, and according to that, the n, then we have L equal to n minus 1. So this case, according to the value of L, so that can be equal to 0, 1, 2, 3, as well as 4, or any higher. Then the corresponding atomic orbitals are called as S, P, D, F, G, H. So S orbital corresponding to this case when L equal to 0, and the P orbitals when the L equal to 1, and L equal to 2, that will be D orbitals. Now you probably have learned what is the shape of each atomic orbitals, right? So that's kind of, we use the model again here. So let's see that what the atomic orbital looks like. So this one is the S orbital. So you see that the S orbital is a spheric. Where this P orbital, so the P orbital, there are 3 P. So that's we call PX, PY, PX, PY, and the PZ orbitals. And each one are perpendicular to each other. So like you can think about the X, Y, Z axis. X, Y, and Z axis. So are perpendicular to each other. And the 3 orbitals have the same level in energy. So they are degenerate. As when you go to the D, then there are 5 D orbitals. You can see those 5 D orbitals. Although those 5 D orbitals are in different shape, well, these 4 are in similar shape, but this one's different shape. But they are the same in energy. Then once you go to the F, you see there are 7 F orbitals. All the 7 F orbitals, you can see that some are in the similar shape, but some are different, quite different. But they are the same in energy. Then we look at the G, you can see here F orbital, there are already 7. So G orbital, it will increase by 2. So there will be 9 G orbitals. So let's see that. You can see this will be the 9 G orbitals. You can see here 5 and 4 plus the total of 9, right? So those are the atomic orbitals. For the atom, you know that they will fill the electrons. Let's say that Lewis atomic models. So we will assign the electrons to orbitals. We first fill all the orbitals of similar energy. This will be Hund's rules. Before pairing with another of opposite spin in a half-filled orbital. So this will be the Pauli rules. Example here, like we said, the carbon atom. So carbon atom has 6, so carbon atom, so atomic number 6, right? So you can see that we will say 1s, so 1s, then 2s orbital has energy higher than 1s. Then there are, so s and p, so 3p, right? P orbitals. So you will fill each orbital fill up to 2. So s orbital energy are lower than any of those orbitals. So you need to fill those 2 in opposite spin, right? Fill that, then for the 2s orbital. 2s orbital also in terms of energy also lower than the 2p, so the 2p orbitals. In this case, we will fill 2s like this. Then you come to fill the 2p orbitals. Now you have 6 electrons in total, already used 4, right? So only 2 left. In this case, we will follow this one, the orbital of similar energy. First fill all of them, so you will fill all of these orbitals. So you will fill like this. Then instead of pair them up, so this case, this will be the electron configuration of the carbon atom. Now if you go to nitrogen, so let's look at the nitrogen 7. Nitrogen 7. So if the nitrogen, so you have 3p orbitals, so you will fill each, right? Then you go to the oxygen, that's 8. So then that's 3 half fill, then 1 more fill up to here. So that's will be, let's say the oxygen, you will have a configuration, fill this one, then another one fill. So this will be the electron configuration of oxygen. Now, the order, if the atom is larger and larger, what's the order we fill? For those small atoms like carbon, nitrogen, oxygen, fairly easy, you just follow this order. But for the higher, you can see this one. This will be the order we will follow. You will fill the 1s first, then we fill 2s just like we did here, 1s, 2s. Then you will fill 2p, right? So we fill 2p, then after that you fill 3s, then 3p. Now, 3p supposedly you should fill 3d, but you will go 4s first, then you go to 3d. So that's the exact case for the transition metals. Now you can see here, we still see the rules works for the Hund's rule and the Pauli's rule. For example, when we look at the copper atom, so we have 1s2, 2s2, right? And 2p6. Then we have, so 2s, 2p, so 3s, right? We will fill the 3s, 3s2, and 3p, also 6. Then we have d, right? So 4s, 3d. Now for the coppers, you can see in this case, coppers, suppose you should fill the 4s2, then you go to the 3d orbital, and there are 9 orbital 2. But this case, the d orbital is missing 1, so you need to change them. So let's change the color. So the copper will be 4s1 and 3d10. Right? So this is the only exception. Other elements will follow this pattern. So if you look at the periodic table, in the same group, so copper silver will follow some trend like this. Okay, let's look at the Lewis atomic models. The Lewis model involves recognizing that not all electrons in an atom play a role in chemical bonding. Well, let's look at this carbon atom. When carbon atom is used to form the bond, you know that there's a 1s orbital, right? And the 1s orbital quantum number equal to 1. So this is the inner shell. So inner shell will not involve in the bonding. So only the valence shell. So this case, that's how not all electrons in an atom will play a role in the chemical bonding. So for the carbon, actually only the 2s2, 2p2 electron will participate in forming the chemical bond. So the outermost electrons of an atom, this case we call valence electrons, are chemically important and are treated with the Lewis models. In this case, Lewis model will consider each electron considered as a dot, so very small. So in this case, if you draw the carbon atom, carbon form the bond with oxygen, for example, carbon dioxide, right? The carbon atom, we will say outside 2 electrons, right? And oxygens, outside, like we draw the outside 2, 2, 2, so 2 to 6. So we will draw them oxygen like this, right? Carbon dioxide. In this case, this will be the Lewis model of carbon dioxide. Now, if you look at this case, well, we should draw another way. So carbon dioxide, Let's draw this one. Now in this case, you can see each atom are surrounded by 80 electrons. So look at this one. So this oxygen has 2, 2, 2, 2, so total 8 electrons. And this oxygen also, you can see that 2, 2, 2, 2, so the total 8. Now if you look at the carbon atom, so also that's, so here's 4, so also 8. So in this case, the Lewis model, that tells all the atom here inside the carbon dioxide has 80 electrons. So 80 electrons for the valence shell. So this one, that all the atom meet the 80 electrons. So we call octet rule. So this will be stabilized. So that's octet rule. So this states that atoms tend to form compounds in ways that give them 8 valence electrons. And so the electron configuration of the noble gas. So if you check the periodical table, all the noble gas of the periodical table, their valence shell electrons are 8. So they are so stable. So that's how, for those noble gas, like we mentioned, noble gas, for example, here, helium, this is the exception because the valence electron only 2 electrons, because this is the quantum number equal to 1. So you can see neon, argon, right? All the elements for the noble gas, they're outside, there are only 8 electrons. So they are so stable, so they normally don't react. They can exist as a single atom. So they can exist as single atom. Now there are only a few exceptions. Not all atoms, once form the stable molecules, their outside will have 80 electrons. This exception applies to, say, molecules with an odd number of valence electrons. So in this case, if you see the nitrogen dioxide, and we know nitrogen atom outside only 5 electrons. So you can see that once formed the nitrogen dioxide, you really cannot allow each one will fill the valence electron will exactly limit 8. And also the molecule in which one or more atom possess more than 8 valence electrons. So in this case, you see copper oxide or copper like this one, or copper oxide. And also molecule in which one or more atom possess less than 8 electrons, atomic number less than 6. So those are the exceptions. Now let's focus on the covalent bond. So as we know that the covalent bond example shown here. Now carbon dioxide I already showed you earlier. Let's look at the covalent bond like methane, which is from the carbon atom with 4 hydrogens. So let's say the carbon atom outside 4 electrons, right? We know that because 1 s electron is not. So you have 4 hydrogens. Each hydrogen come here to form the bond. So hydrogen come to form the bond, and hydrogen come to form the bond, and then this hydrogen. So in this case, the pair of electrons, so this pair of electrons, let's focus on this pair of electrons. So this pair of electrons belongs to both carbon atom and hydrogen atoms. So there's no actual electron transfer. Like we say earlier for the ionic bond, for example, if you look at the sodium chloride, in this case, sodium actually lose 1 electron to chlorine, so chlorine form an anion, sodium form a cation, so there's actually electron transfer. But this one, there's no electron transfers. And electrons are shared between the nuclei of the 2 atoms in a bond. So in this case, these electron pairs are shared by the carbon and hydrogen that form the bond. So in this case, we can draw instead of use the 2 dots. So that's a Lewis model. We can draw using the 1 line to stand for 1 pair of electron. So we can draw the structure, and you probably have seen this a lot already. So in this case, one line indicates one pair of electrons. So a single covalent bond is a pair of shared electrons between two nuclei. So this will be the single covalent bond. So that's a pair of shared electrons. Now a double covalent bond is two pairs of shared valence electrons. Like an example we showed earlier, carbon dioxide. So carbon dioxide, in this case we can draw carbon atom, like we said there are two pairs of electrons, right? So in this case, we can draw something like this. So covalent bond is the only type of bonding that creates molecules. These molecules have definite geometry. Now let's look at that here. When we talk about the ionic molecule like this one, the species of sodium cation and chloride anion will be drawn together by electrostatic interaction. Because of those positive and negative attraction. But once you put the sodium chloride into water, so put it into water, then you don't have this anymore. So each one will be separated by the isolated sodium cation and a chloride anion. So that's how for the covalent molecule, like a covalent bond, these molecules, no matter you dissolve in water or others, those bonds are still there. So that's how the covalent bonding is the only type of bond that creates molecules, and the molecule have a definite geometry. So the question is the definite geometry. What means definite geometry? We will look at these geometries by certain rules. That's how we will focus today for the molecular models that help us to figure out what the geometry will be. So according to the Lewis structure for any molecule, you can draw the Lewis structure, right? Then after that, you can calculate the number of valence electrons in the compounds. Then you will connect the atoms to central atoms. So central atom using only single bonds. The atom with the most available sites for bonding is usually placed center for this case. So the number of bonding sites is determined by considering the number of valence electrons and the ability of an atom to expand its octet. Now let's look at the example of sulfuric acid. So sulfuric acid, we studied for that. Now in this case, so we should identify, so we will look at this sulfuric acid, we draw the Lewis structure, right? Sulfur, so we will have this one. So sulfur, remember, sulfur outside, there are only 6 electrons, right? Now, let's octane outside the 6 electrons. So we will draw them something like this. Now, we have another one. So we will have this one. Then we will draw so this will be the Lewis structure of sulfuric acid. Now notice in this case, we know octane outside all you can see that 80 electrons, that this octane also 80 electrons, and this octane 80 electrons. Hydrogen on the first row of the periodic table, which only allows to have up to 2 electrons. So the hydrogen is 2 electrons, and here also 2 electrons. So now we can draw the bonding, something like this case now, convert the dotted to bond. So you can see so here will be the double bond, single bond, single bond, single bond, single bond. You can connect them like this one. Some will be single bond, some will be double bond, right? So this case, then you can see that the ability for atom to expand its octet. Now this case, you can see sulfur outside how many electrons? So the valence. So here is 4, 4, and here are total 4. So total are 12. You can see that this case, that means the sulfur will not follow the octet rules. This is because the sulfur has a d orbital involved. So that's expanded the octet rules. Now place remaining electron as non-pairs to fill the octets of as many atoms as possible. So in this case, you can see oxygens, we know this not share with the other atoms. So this one actually will be non-pairs, like this are non-pairs. So for this one's non-pairs, and this one's non-pairs. So fill the remaining octet by making multiple bonds, making a non-pair of electrons located on the more electronegative atom, and into a bonding pair of electrons that is shared with the atom that is electron deficient. As we show the sulfuric acid, we know that you will see make a multiple bonds. We draw that, right? Let's draw again. So this case will be double bond, and this case double bond and oxygen. Right? So we have that. And check that you have the lowest formal charge possible for all the atoms without violating the octet rules. So what means the formal charge? Formal charge is where you can calculate, follow the rules like valence electrons minus half of bonding electrons minus the non-electrons. Let's look at this oxygen. Oxygen, that's one. The valence electron, we know valence electron, that's total 6, right? Minus half of the bonding electron. So bonding electron here, the total of what? Of 4, right? And then minus non-pair electrons. So non-pair, we have one non-pair and two non-pair, so that's minus 4. So equal to 0. Check that the lowest formal charge possible. So supposedly, if the molecule are stable, you should allow every atom has a formal charge of 0. So this case, that meets this condition. You can see that, right? So you can calculate the hydrogen. You can see hydrogen valence electrons 1. So for hydrogen, valence electron 1. And minus half of bonding electrons, that's 2, right? And the non-pair, there's no non-pair. So this gives 0. Now the questions, the Lewis structure, well, you can see Lewis model that help us to draw the structure, but there are several limitations about the Lewis structure or Lewis models. So Lewis model can provide us intro level about the structures, but really if you try to use the structure to explain many of the physical properties or reactivity of the molecules, that's impossible. That's how right now we normally don't use the Lewis structure anymore. Let's see what's the limitations. Here I list 2 of them. So one of that is the Lewis structures do not indicate a molecular shape. So remember, we care about the models because the model can tell us what's the geometry or image or the shape the molecule have. So here the question is, if you draw, for example, this is the case, it's a dichloromethane for this case. You can see that we can draw the Lewis structure like this one here. This one bond means a pair of electron, right? You can draw them as 2 dots. Likewise, 2 dots, right? You can draw this way. Now, but we can draw a bond. So this is the structure. You can see that this will be the model that tells the 3-dimensional structures. But you can see this case, if you draw the Lewis structure, indicate the 2 structures are different. Because in this case, the 2 chlorine are opposite side and 2 fluorine are also on the opposite side. And for this case, the 2 chlorine are adjacent on the same side and the 2 fluorine are the same side. According to the Lewis structures, they should be different. But as a matter of fact, they are the same. So if you look at the structure, this model, and in this case, you see this one will be chlorine. So the yellow will be chlorine and this will be fluorine. And you can see that these 2 that will be drawn in this way, showing that they are opposite. If you look at it here, they are opposite. But you rotate them, so twist like this way, you see they are on the same side, this on the same side, right? So that's how we really needed to use the model like this one to tell us the real structure of the molecule, so that we can look at the spatial arrangement about the atoms within the molecule. Another limitation about the Lewis structure is the Lewis structure fails to predict the paramagnetic property of oxygen. So what means that? You can see In order to have the paramagnetic properties, the molecule must have unpaired electrons. So that's unpaired electrons. So the molecule can be paramagnetic. Now, if you draw the Lewis structure of oxygen, we can see oxygen outside 6 electrons. So in order to meet all the oxygen atom has 80 electrons, so we can draw something like this, right? Now, in this case, you can see all the oxygen atoms will be 80 electrons, like this case, 80 electrons. And so here, 80 electrons, right? So 8. So you don't see there's a single electrons somewhere, right? As a matter of fact, the oxygen has 2 unpaired electrons. But if you use the Lewis structures, you cannot draw the structures for the oxygen, even that's a very simple molecule like the O2. And that's the one we breathe in air. Well, basically, when we breathe in air, we actually breathe in the oxygen. And the oxygen is, once we breathe in our lung, and that will be transported by our hemoglobin, that's transferred to the tissues that provide the oxygen to do the oxidation reactions and to do that, so to continue this metabolism of the cells, so that allows cells to provide energy for meet our daily usage. So right now we have the coronavirus, COVID-19 infections. People have the difficulty to breathe in the airs. So that's how those people are ill. The actual structure of oxygen, you can only explain by the molecular orbital. Molecular orbital theory. That clearly tell oxygen has 2 unpaired electrons, so that how, and you can see how to check them paramagnet or diamagnet. You can see, watch these videos, and this video tells you if the oxygen is paramagnet, if you cool down, convert the oxygen to the liquid oxygen, then this liquid oxygen will be absorbed to the magnet. If you compare with nitrogen, there's no pair of electrons, so nitrogen will not, even that convert nitrogen to liquid nitrogen will not be drawn to the magnet, but oxygen will be. Now let's look at the bond polarity. Remember, every atom, once they form the covalent bond, just like we see the example earlier, like a methane, right? Carbon, hydrogen form the methane. We will talk about the polarity. We know the covalent bond is because the 2 atoms share this pair of electrons, right? Now, each atom has a different scale or different capability to draw the pair of electrons. Remember, every atom want to meet the octet rule. So they try to draw the shared electron to their valence shell so they can meet the octet rule. So the electron negativity are assigned values that measure the tendency of an atom and how they attract the bonded pair of electrons. So the scale of electron negativity changes from 0 to 4. 4 will be the largest, and 0 will be the smallest. So the larger the electron negativity value means the atom has a higher power to draw the pair of electrons once they form the covalent bond. So in this case, the carbon atom has the electron negativity about 2.5, and hydrogen has 2.1. So in this case, you can imagine carbon atom has a higher power to draw the pair of electrons. So in this case, the pair, so if we draw the electron pairs. So this pair of electron so this case, I simply draw them as bond here, right? Just to show one pair. And hydrogen. Now you can see this pair of electrons will not reside in the middle of the bond, actually more close to carbon. So it's not in the middle. So this bond shows some polarity. So this case, we can draw the bond, something like this. We use this one, show an arrow, indicated towards the electron, move the direction of the electron to move. So we draw that, show that there's a dipole. So this case for the bond dipole. And the bond dipole, you can calculate them according to, so this is the difference of electron negativity, right? And multiply the bond length. So this case, let's say the bond length, then multiply by a factor. So this one is 4.8. So this way we will calculate the polarity of the bond. You can see that the larger the bond length, also you will have a larger the bond polarity. But the more difference of the electronegativity, the bond will be more polar. Now the electronegativity values are tabulated for the elements. So in the periodic table, electronegativity increase left to right and from bottom to top. I will show you a table about the periodic table that lists all the electronegative values on the next slide. So we can draw an arrow from less electronegative atom to more electronegative atom in bonded pair to establish a bond dipole. So this case, like here, we can draw this case, right? So that shows the bond dipole. So for the nonpolar bonds or no bond dipoles, these are shared equally between the atoms. So this case, if the electrons are equally distributed between the two atoms, we call this a nonpolar bond. Nonpolar bond. So this case applies for the difference about the electronegative values. It's from 0 to 0.39, but check these values. It's a variable according to different source you use. Some textbook use 0.5. Because this case, look at that, that's a 0.4, right? So if we apply that, we know this bond are nonpolar. That explains why all the oils you're using, that typically oil or lipid molecule, you think about that, or fat, because they are formed basically is by the carbon hydrogen, and their difference about electronegativity is 0.4. So this case, we will consider them as nonpolar. And because they are nonpolar, so they are not mixable with water. Now, if you compare, let's look at the water molecules. Water molecules, this case, right? And we have oxygen. So we have a pair of electrons, non-pair electron like this. And then oxygen, so electronegativity is 3.5. Hydrogen 2.1. You can see the difference is 1.4. So that's how this one is polar. That's how water is polar, which is so polar that can dissolve sodium chloride. So sodium chloride, even ionic molecule, they can dissolve that. So the polar bond, you can see that electrons are not shared equally between the atoms. So the difference of electronegativity can from 0.4 to 1.7. So this case will be unequal sharing of the electron pairs. Let's look at the water again. So for the water, let's do this case. And you can see this, the pair of electrons, because of the so big difference between the electronegativity of oxygen and hydrogen, so that makes in certain time, this electron pair actually reside close to oxygen. So this hydrogen actually is naked. So that's how for this case, sometimes you can see that reach the equilibrium to form actually this anion and the proton positive. You can see that's how earlier we started for the water with the pH, the neutral water pH equal to 7, right? That because in neutral water, there's a certain level of the water actually dissociate to give this one, and the concentration of the proton that equal to this much molar. So that's how we have a pH equal to 7, right? And this explains why this bond can dissociate, because the electron pairs move more close to oxygen, and the hydrogen is feel like naked. And this reach the equilibrium, right? Now this will be the table about the electronegativity. As we mentioned earlier, for the electronegativity from the same row, from the left to right, you can see that the increase, right? This one's the increase. That's how fluorine is largest, and this carbon's 2.5, hydrogen 2.1, and also increase from the bottom to top. You can see bottom to top, right? And you can see this trend also bottom to top. Now, some cases here, there will be some difference. So these transition metals, we have to use different theory to explain them. Remember, we said we needed to finally to figure out what's the geometry of the molecules. And earlier we used Lewis structures. We said Lewis model cannot tell us the geometry of the molecule. So here we have to use this series, VSEPR models. So this means valence share. So valence share, electron pair, repulsion. So that's how we simply abbreviate that as VSEPR. So the valence share electron pair repulsion model. Why they repulse each other? And if you look at the structure of the methane we saw earlier, so this will be a pair of electrons, right? And we have a pair of electrons, and a pair of electrons, pair of electrons. Now remember, all the electrons actually carry negative charge, right? So this one's negative, and this negative. If they put them together, so this angle, so let's draw again. So this will be bound angle. So this is the bound angle. Now, if the bound angle is too small, then they will repulse each other. So every bond try to stay away from each other as far as possible. Now, however, if these two bonds are stay very far, for example, maybe you can put them linear in the opposite side, then the distance between this bond and that bond will be getting closer, right? So the overall, that will you have to compromise to allow all the bonds stay away from each other as far as possible. That's the rule allow us to figure out what's the best geometry in three-dimensional structures. So that's how we will explain that. So this model will help us to determine the best Lewis structures. So in this case, you will identify the number of electron groups here. Electron groups present around the particular atom. This atom often that is central atom or atom of interest. So if the molecule are smaller or very simple molecule, we will call them as a central atom. Example like this case, like the methane, right? Carbon atom, central atom. We look at that. But there, the atom of interest, if you see the structure like sulfuric acid, for example, we draw structure of sulfuric acid, right? Now, when we look at here, how these four bonds are arranged, so this will be the atom of interest. But when we look at the angle of here, this bond, then this atom will be the atom of interest. So each non-pair of electrons or non-bonding electrons counts as one electron group. So this case, look at here, non-pair of electron, like this oxygen we mentioned. So this, look at here. This oxygen has pair, so there's two more pairs, right? So two more pairs. So each one will consider as one electron group. So you have 1, 2, 3, 4. So that's four groups of electrons groups. Now each bound atom counts as one electron group. So in this case, this is the one bond, so as one electron group. So regardless if bonds are single or multiple, like this case here is double, you also consider as one electron group. This one electron group. So this one electron group. So you are establish the electron group shape and the molecular shape based on the number of electron groups. And in this case, we have this will be the central atom, and this case is a bonded atom, right? And this one will be here non-bonding electrons. So you will calculate the total number of n plus n, right? So this molecular shape is the lowest energy arrangement of the electron groups that can minimize the electron pair repulsion. So you have to come with a geometry that allow each pair of the electron groups will stay away from each other as far as possible. So let's look at the examples here. You can see that atoms or electrons like to be as far apart from each other as possible without disrupting the symmetry drastically. Non-pairs take up more space because they are not confined by bonds. So look at the example we show here. Like this is sulfuric acid, we see example. You will see that oxygen, we focus on the oxygen here. You have one pair of it, non-pair electron. Here is non-pair electron. So there are four, right, electron groups. In terms, so those pair electron will be confined between the sulfur and the oxygen. Likewise, this pair of electron will be confined between the oxygen and the hydrogen, because that's the covalent bond, so that can link the two atoms together, right? And in this case, the non-pair electron, there's no more additional atom come here to share with this pair of electrons. So they are not confined by bonds. So in this case, they are more polarizable, or they are loosely held by this oxygen atom. So in this case, they will occupy more space than this pair of electron. So because of that, the repulsion, you can see the non-pair electrons, those will be larger than the non-pair and the bonding. So this repulsion here will be bigger than these two, and those two will be bigger than the bonding electron. So because of this rule, when you try to draw the structures and you arrange all possible electron groups in the three-dimensional space, then you need to think about how to accommodate all those orders, allow them so each one, so you can either arrange the non-pair electron on the which position that allows those repulsion to be reach the minimal state. So for the simple molecular geometry, the simplest one probably is the two atom. Like this case, two atom, right? These two atoms, so here show the two different atoms, like a hydrogen chloride. So these two, they are so simple, you don't need to worry about how they arrange. So that's basically linear structures, right? This is very simple. And so there's more example. If the two atoms are the same, for example, hydrogen, right? So they are the same. So that would be the linear geometries. Now let's move on to see a little bit more complicated. As three atoms can be like this linearly. In this case, you can see can be the carbon dioxide. So you can see one electron groups, another electron groups. So when the center atom, there are two, they try to stay away from each other. So they're on the linear, so the bond angle will be 180 degrees. So this case, that will be farthest away from each other. So that's a linear. Another example like this barium, so dichloride. Also, you can see this center atom with barium and two chlorine on the other side. So let's see that a little bit more. When you have say this case, so AX3 molecule, this type. Now this type, there are three bonds. So each one can stay away from each other. So this case, the bond angle will be 120 degrees now. So example like the boron trifluoride. You can see example. For this case, if you have some molecule like this one, but so one bond actually is non-pair electrons, then you will have these banded structures. Something like this will form the banded structures, right? And remember, here we only show the bond. Remember, if there's a non-pair electron, for example, if you have a non-pair electron, but a non-pair electron, and in this case will be the structure of water. And the non-pair electron will not hold the bond angle because here is no bond, right? We mentioned covalent bond is between the two atoms share this pair of electrons. So this case, this bond, now remember, if you talk about the covalent bond like this one, so four electron groups should be tetrahedral geometry. So tetrahedral geometry bond angle the perfect one like we saw in the methane. So that's 109.5 degrees. So you can calculate, find from the Google, you may find that there are 3 different methods to calculate why the bound angle is 109.5. Now, as we mentioned that because of the repulsion from the non-pair and the non-pair are bigger, so in this case, actually, so this take more space, so that squeeze this bound angle, make this bound angle right now reduced to only one. You can see this one. You see this one, talk about the tetrahedral geometry. So that's where you have 4 pair of electron groups. In this case, it will be 4, right? You look at them from a different angle. So this will be the tetrahedral geometry. Tetrahedral. So they will form this tetrahedral. So 4 electron groups, you can see that. Think about it. If this is the structure of if one bond is occupied by non-pair electrons, it's not a covalent bond. So example like NH3, ammonia. So ammonia, you can see in the nitrogens. So nitrogen outside is 5 electrons. So you can use 3 electrons to form the bond with 3 hydrogen atoms, right? But you still have 1 pair of electron here. So this will be the ammonia. Now you can see that actually, so this is the pair of electron. So actually 4 electron groups. So if that's 4 electron groups, that will be tetrahedral. Now in this case, you can see that actual geometry is kind of the pyramid, like this one. So the nitrogen and the 4 hydrogen atom here, and this will be the pair of electrons, like this case. And you can see this one here, because of the non-bonding and the bonding repulsion are actually bigger than the bonding. So this bond for bond angle here still is not a perfect 109.5 degrees. So this will be the geometry of ammonia. For the case of here, if 2 of the bonding pairs are non-pairs, like the case of water. So you can see the water case, oxygen, right? So 1 pair, and another one go here. This is the oxygen, right? Fill with the hydrogen and the fill bond with hydrogen. So you have a non-pair and a non-pair. So that's how what go to this geometry, like this one. So that's how when you draw the structure of water, you should draw something like this. It's bended. Never draw water molecule like this one. So never draw that, because the water molecule cannot be linear. Now, if there's a 5, like this case, 5 will take this geometry. Now, you can see that we'll have 2 cases. Now, if there's a 5, if all the 5 bonds are the same, then you can draw the either state structure or that kind of structure. You see, this will be the axis. If here, now notice this will be axis, and this will be equatorial axial bond. So remember, if you see that, so this one's moving, let's move on another one. This will be the for the 5 electron groups, right? 5 electron groups. If they are the same, like all the bonds are the same, then in this case, it doesn't matter you put it anywhere, right? Like the example of the PCl5. So that's 5, that phosphorus and 5 chlorine, right? So you can have this geometry. Now imagine if one of them is a non-pair. If one of them non-pair. Remember, for those horizontal, we call them as equatorial. This bond angle is 120 degrees, right? And this bond angle here is 90 degrees. So if you have non-pairs, you better put the non-pair. So put the non-pair on this position, under this position. So in that case, the non-pair will have 2, which is you see. So if we assume 1 non-pair, so you will put it here. So say this is a non-pair. We mark this as different color. Now you have 120, but 2 90. If you put this one as a non-pairs, then you will have 3 of them will be 90 degrees. So this repulsion will be bigger than that. So better to put this, in this case, you will have a geometry of that, like this case, right? So you will have the geometry like this one. So this we call geometry of the seesaw shape. Right? Remember that. Now, if you have 2, then you will put the 2 on this horizontal. So you will have a T shape. So the geometry will be something like this. So we call T shape. If you have 6 pairs, then this will be octahedral. And you can see this case all are 90 degrees now. Now, if that's the case, if you say one of them, think about one of them, so this one will be symmetric. So if one of them will be the non-pairs, you can put a non-pair here. So this will be square pyramidal. Now, if there are 5, then you will put 5 like this way, right? 5. So here will be the summary about all those geometries. Say, if there are 2 electron groups, will be linear, right? The bonds, 2 bonds, non-pair, no. So this we will call the molecular series, so the AX2 series. So the molecular shape will be linear and the bond angle 180 degrees. So this case can be, if depending those atoms are the same, can be nonpolar, but possibly bipolar. So this hybridization will be sp. So if the central atom is carbon, so that will be sp, hybridization. We haven't talked about the hybridization yet. Hybridization means, say, for example, we have a carbon atom. Remember, carbon atom have a 2s, right? And a 2p. So if we fill the electron like this, now notice that the 2s orbital and the 2p orbital electron are at different levels. So 2s orbital electron energy are lower than the 2p orbitals. If you just use this atomic orbital to form the bond, you can see this one already failed. So you should know this will not form the bond. In this case, the carbon will only form 2 bonds, or possibly form 3 bonds, because this can accept a pair electron from other atoms. So, but even for this case, let's say form the bond of the methane. So 4 bond with hydrogen. You can imagine 1 pair electrons will come from 2s, form the bond, and you can see if this is the case, then the 4 bonds should not be the same. So this 4 bonds should not be identical. So some bonds are longer, some bonds will be shorter. But this one is not the case, right? The experimental results tells all the bonds are the same. You really cannot tell which bond is longer than the other. So that means there must be hybridized. So that in this case, they will move to a different way. So in this case, the 2s and the 2p orbital will be mixed to form the 4 identical orbital now. So 4 identical orbital, each one has 1 electron in this case. So then each one will form the 1 bond with the hydrogen. So that's how this one we call sp3, because 1s orbital and 3p orbital all hybridized. So that's we call sp hybridization. Now let's look at the sp hybridization. So sp hybridization, remember for the p orbital are all px, py, pz are perpendicular to each other. This sp, that means you only allow 1s orbital move to the p orbitals. So notice that this case we will have so these two will be, these two are 2p, which is not hybridized. Another p orbital will be lower a little bit here, and the s orbital will be moved to at the same level like this one now. So this will be sp hybridized orbital. So 1 electron excited to the empty orbital of the p orbital. So this will be sp hybridization. And using these two to form the bond, right? Form the bond. And in this case, this will be the linear because those two are perpendicular to each other. So that's how you can see that once you use the SP, you will form the linear geometry and allow the two pair of electrons. One will be in this direction, perpendicular to each other. Another one will be in this way, also perpendicular to each other. Now, for the trigonal planars, you can have 3 bands in this case. So we have AX3, so trigonal planar, so that band angle will be 120. In this case, so sp2 hybridization. So what means sp2? So you will allow this one electrons excited to the p, allow the two p orbital and this one s orbital mix to form the 3 orbital at the same level, but another p will be not changed. So in this case, you will have a trigonal planar and the unhybridized orbital will perpendicular to this plane. Now another one, this case is trigonal planar. So this geometry supposedly electron group shape, right? But there will be one lone pairs. So this case we have AX2E. So this will form the banded. So you will have this one. So in this case, that will be polar. This will be the polar structure, right? So because in this case you have electrons, but this one is not confined to between the two atoms. Now for electron groups, we know that's tetrahedral, right? So the tetrahedral can be this one 4, that's tetrahedral 109.5. So this is nonpolar, this is sp3, as we mentioned, sp3. But for this case, if there are 1, so AX3E, so trigonal pyramidal, so this case, because of the repulsion between the non-pair and the bonding are greater than this bonding pairs. So this one is a polar now, as the bond angle for here is less than 109.5, right? Now, if there are 2 non-pairs, this we call AX2E2. So this will be banded structure, like in the case of water. This is the case of ammonia, right? So you see this case is also less than 109.5. We mentioned that 104.5 actually. Let's move on even higher structures like this one. It's an electron group shape that's a 5. So the 5 you will have this one. So notice that this will be equatorial. So this is the axial and equatorial. Equatorial here. So this you have 4 scenarios. 1 of 5, this case AX5. So that's trigonal pyramidal. So this is nonpolar. So this case you can see that sp3d, right? And this case we know you only have 3 p orbitals, but there's a d orbital. So that's how we have an example like that. Now here, this case, and here you see equatorial will be 120, right? Axial will be 90 degrees. For this case, you have a seesaw we mentioned earlier. One of them will show like these structures. So the bond angle, notice that will be smaller. So this will be sp3d orbitals. And this case will be AX3E2. So then that's a T-shape as I mentioned earlier, right? T-shape. So these are the bond angles with this one less than 90 degrees. Or somehow the T-shape. And if there's a 2, in this case, that's AX2E3, this will be linear, so a nonpolar now, so for this case. Now for the electron group 6, you have octahedral, this case. So you will see them, we basically have 3 scenarios, 6, 5, 4, right, bands. So AX6, AX5E, AX4E2. So octahedral, this one, nonpolar. So this sp3d2 hybridization. And this is square pyramidal for this case, and a square planar. This can be square planar. One example for this square planar is this one. So let's see, platinum NH3, 2. So this one we call them as a cis platinum. And this molecule is a very powerful molecule to treat cancer patients. Let's move on to the large organic molecules. So as the molecule getting bigger, what happened? So in the larger molecules, we talk about the geometry about a particular atom rather than the geometry of the molecule as a whole. So we will move on step by step. For example, we look at the acetic acid, CH3CO2, acetic acid. So the structure will be shown like this one. So here is the CH3 methyl group. That's a carboxyl group, right? So we will look at the geometry of the atom, particular atom. So we will look at this one. So this carbon atom, this case will be sp3 hybridization. So this will be tetrahedral geometry. And look at for this carbon atom, this is the one electron group, another electron group, another electron group. So 3, so that's sp2, right? So sp2 should be trigonal planar, right? And for this case, you have a 1, 2, 3, 4. So that's non-pair. So this is also 4 electron groups, so that's sp3 hybridization. Then this supposedly will be tetrahedral, but there are only 2 non-pairs. So this will be the band, right? So that's how we have a structure like this one. So this one tetrahedral, so 109.5 here, but this trigonal planar 120, and this one's tetrahedral, but this one supposedly cannot be 109.5, less than that, because of the non-pair pair repulsion are bigger. So this one's less than that. Now the questions, since for the larger molecule, if we look at the atom, particular atom individually, so how do we get the whole image about the molecules? So this structure of the whole molecule is only clear when we look at the whole molecule. So if you look at the whole molecules, in this case, there will be no atom of interest anymore. So you have to see how those groups are arranged together. So, but the geometry about each atom still follow the same rule we described above, but the whole geometry, we will put them together. So this case gives us the whole geometry. Now let's look at some examples here. This geometry, this structure will be the one drug molecule we call codeine. Codeine, people use drug, so this is structure of codeine. And so you can see that it will be different atoms put together. That will take an overall geometry like this one. And this will be the structure or geometry of nicotine. And we know nicotine is people smoke, so that's take the nicotine. The structure will be like this, right? And then let's look at the structure. This will be the sucrose. This is the table sugar. You can see this will be the overall geometry of the molecules. And you can explain them the property of this molecule according to the shape. For example, here, this is the sucrose. You can see this bond here. Those bonds join them together. And you can see this bond. You can hydrolyze them according to this bond and hydrolyze them and break them to glucose and lactose. So let's look at the molecular polarity. Earlier we talked about the bond, right? Each bond has a polarity according to the difference about the electronegativity. So the compound is nonpolar when the structures, so let's look at that, composed of single elements only. So this case like a hydrogen, single elements, chlorine, or like oxygen, or nitrogen, or but for those that you see only a few examples on neutral or nonpolar. So for this case, and all bond dipole are such that the difference of the electronegativity less than 0.4. Example, all those hydrocarbons. Hydrocarbons. Example like we mentioned that CH4 or even kind of oil. You have oil molecules. And also all bond, you have even their difference about the electronegativity is greater than 0.4, so indicate individual bonds are polar, but they can cancel out, so the compounds are symmetric. So let's see the example here. So So the polarity of other compounds is the vector sum of all bonds. So let's see that example here. We will see two examples. This one is a chloroform. So this is a chloroform. And this example is a carbon tetrachloride, CCl4. Now notice that even you look at the individual bond. So we know electronegativity of carbon atom is 2.5, chlorine is 3.16. So if you see that the bond, you have a bond polarity goes this direction, right? Because the difference, you look at that, the difference delta En equal to 0.66, which is greater than 0.4. So this bond is polar. And this bond also is polar. And so electron density, we will say towards the chlorine. So this one has direction. Now, if you consider each one as a vectors, so the three vectors, you sum them, you should have a vector go to opposite to the top, will be in the same strings, and but the opposite direction. So this can cancel out. So in this case, this one can cancel out. So this one is a symmetrical structures. That will be the nonpolar molecule. But for this case, you can see that we still draw the polarity go here, right? Polarity go here, and this polarity go here, this polarity go here. So overall, you have a polarity go this direction. But for here, carbon and hydrogen, even though this one has electronegativity less than 0.4, we can consider this one's no polarity, but overall the molecule has the polarity goes this direction. So this chloroform is a polar. You can see the polarity, this one has a polarity of 1.8, have a polarity of this much. Overall, we will come to the end. We will study why we studied the molecular model. We care about the molecular polarities because this one strongly affects several physical properties of the molecules. All those properties can be affected by different interaction between the molecules. Let's look at that. If they are, so let's see what type of force between the molecules. So let's look at the polar molecule, just like a chloroform, right? So we consider making the molecule simple. So this one is a simple molecule. You can see this case will be one end positive, one end negative because of the difference in distribution of electron cloud, right? So if you have another molecule in this case, then they will be oriented in such a way allow the negative side facing here, the positive side. So these are the dipoles, right? So you will have this interaction. So this we call dipole-dipole interaction, right? Dipole-dipole interaction. If there's some molecules, say we have in other scenarios, we have a dipole. So for example, this case, but you have another molecule which is symmetrical, it's non-polar. So this will be non-polar. Because of this electron here, and this molecule is nonpolar, supposedly electron will be evenly distributed around these molecules. But because this one has some positive, they can change the electron distribution of this molecule, allow this area can develop some of the partial negative charge. And so this case will be have a partial positive in this case. So this interaction will be dipole and nonpolar, right? So interaction. Now, another cases for the molecules like a neutral, both are the neutral interaction. Like those, say helium. Helium is an atom, right? The electrons are evenly distributed. The questions for the electrons are quickly move inside the atom. So you can see because the move very quick, there's one instant the electron will move to this area. So the two electrons move to this area. And so this area will be no electron. So you can transiently develop a positive charge on this side. And so this case you will have a transient negative charge. And because this one and the helium nearby will be affected by this uneven distribution of electrons, so here you will generate even slightly partial positive, so they can draw interaction. And so this side will be negative. So this one is a kind of a van der Waals interaction. So this we also call, so there's three, we can combine them to as a van der Waals interaction, but in particular this one we call the London disperse. So all those interactions depends, look at here. The stronger the interaction will be the two molecules be strongly held together, right? So if the interaction is smaller, so the two molecules cannot be strongly held together, so they can be separated. So in this case, we will see their physical properties. Let's look at the first one. So intermolecular interaction between the molecule, we already show here. Then we will look at the melting point. So what's the melting point? Melting point, that's the one is to measure the phase change from the solid. So solid go to liquid. That's the where the temperature, when you have a liquid and a solid reach the equilibrium, the coexist that temperature, measure that as a melting point. When the molecule will stay in the solid, all the molecule like packed together, there will be strong interactions somehow, right? But if the interaction is stronger, in order to form the liquid, notice the molecule, if they stay in the solid, all the molecule cannot move around. So they will be fixed to the crystal lattice. But for the liquid, molecule can easily flow around, so move around, so have more freedom in motion, but the interaction will be smaller. So in this case, you can tell the stronger interactions, higher the melting point. Likewise, for the boiling point is where you change from the liquid to gas phase. And we know the distance between the molecule in the gas phase are much larger, right? So the molecule interaction are smaller. So in this case, when the intermolecular forces are stronger, the higher boiling point will be, right? Another one is talking about the solubility. When you have the molecule dissolving another one, for example, you have a sodium chloride, right, dissolving water, another one dissolving acetone. Water are polar, right? And you can see the sodium chloride can easily dissolve in water, but not easily dissolve in the acetone. Because in water molecules, the sodium chloride, they have the charge, like this charge, right? So they can be easily dissolved for that. Likewise, we say ethanol or methanol, like this methanol, right? Here, CH3, oxygen. And we know this, the polar molecules, non-pair electrons. So the methanol can be easily mixed with water. But if you see methane, non-polar molecules, so this one cannot dissolve in water. That's how you have oil. Those oil you cannot mix with the water. But if you have alcohol, you can easily mix with water. So you can drink like a beer, wine, has a different level of alcohol inside. That will be the solubility, where basically it's like dissolves, like. So talking about their polarity, polar solvent dissolves the polar molecule, non-polar solvent dissolves non-polar molecules.